In this video, I'm going to be going over the solution to problem 10 on the 2024 AIME 2. So the problem says, let ABC have incenter I, circumcenter O, in radius 6, and circumradius 13. Suppose that IA is perpendicular to OI. Find the product AB times AC. Okay, so let's start off by drawing a diagram. So this is a sample diagram we could use. For now, we're only going to focus on this triangle ABC. Don't worry about the point D or the point L for now. We're only going to focus on this triangle ABC and see what we can do with it. So first of all, the problem is asking for the product of AB and AC. So we can denote these two side lengths with variables AB, and then we can maybe call this base here side length C. So we can let this be C. So now, what can we say about this triangle side lengths, and can we maybe relate these side lengths to numbers? Well, it gives us the inradius and circumradius, so both are pretty helpful if we knew the area of the triangle. So let's maybe denote the area of the triangle as A. So A, capital A, equals area. So we know by the formula for area of circumradius, like area using circumradius, that ABC over 4 times the area is equal to the length of the circumradius, or 13. This comes from the extended law of sines. So yeah, that's where the 4r comes from. And then we also have that the in radius times semi-perimeter is going to be equal to the area, right? Because the in radius splits this triangle into 3 equal triangles, all with height r. These all have a height of r. So if these all have a height of r and a base of these different side lengths, it's just going to be a over 2 times r plus b over 2 times r plus c over 2 times r. So it's just the in radius times the semi-perimeter. So if we have in radius times semi-perimeter is going to be equal to the area, then we can just rearrange, saying that a plus b plus c over 2a is going to be the length of the in radius, which is 6. Okay, now what we need to do is we need to figure out how a, b, and c are related. Are they related in any way? Well, that's where this point D and L come from. So L is just simply the point where this circle is tangent to BC. Not really important, but point D is pretty important because what we did is we took AI, which keep in mind is a perpendicular bisector, right? Because the incenter is the intersection of perpendicular bisectors. Angle bisectors. These are all angle bisectors, my bad. So what we did is we took this angle bisector and we extended it to meet the triangle here, meet the circle here at point D. So if this is an angle bisector and it's meeting the circumcircle here at point D, then we know that this point here is bisecting this arc BC into 2 equal arcs. So these arc lengths here are both equal. Okay, so now we can say something pretty cool about point D. So we can say that point, so we want to kind of find like some relationship involving this point. So what we can say is that this is my claim. My claim is going to be that these 3 side lengths here are all equal to each other. And it's actually pretty easy to prove, right? To prove that these 3 side lengths are equal to each other, we just need to prove that these 2 angles are the same and that these 2 angles are the same. So let's first focus on angle IBD. Right, what is angle IBD? Well, angle IBD, if we call it x, then this here becomes 180 minus x. So now, what do we need to add up to get to x? Well, to add up to x, all we need is alpha plus gamma, right? These are our 2 angles. So the value of x is alpha plus gamma. So x equals alpha plus gamma. Oops. So, okay, and then now what about this angle here? What about angle DBI? Well, DBI is just going to be alpha plus this angle DBL. So angle DBL, right, what arc does it subtend? Well, angle DBL subtends this arc here, arc DC. And angle gamma also subtends the same arc, so that they're both equal, right? So angle DBL is equal to x. So these 2 angles are equal to each other. So we have that angle DI is equal to the length of ID is equal to the length of BD. And we can do something similar for finding that these 2 lengths are also equal, right? By similar logic, this angle here is just going to be beta plus gamma. And then this angle here is also going to be beta plus gamma because if we're subtending this arc here, then gamma also subtends that arc. And then beta is just going to be added onto that. So now we have that these 3 side lengths are all equal to each other, right? Okay, so now what else can we really say? Well, note that note that IA is perpendicular to OI, right? So this is pretty valuable information because what we can do is we can make ourselves a neat little isosceles triangle here. Since O is the circumcenter, we have that these 2 legs are equal to each other, so therefore, by hypotenuse leg congruence, right, we have that IA is equal to ID. Because it's an isosceles triangle's altitude splitting its base into 2 equal lengths. So we have IA is equal to ID. Now look, ID is also equal to BD, and BD is also equal to DC. So now we have a lot of side lengths equal to each other, which is going to be pretty helpful. So now we see that this whole quadrilateral here is cyclic, right? Because the whole thing is subscribed in this circle. So we can intuitively apply Ptolemy's theorem, right? Ptolemy's theorem says that the product of the diagonals, which in this case are AD and BC, right? These are the diagonals here, is equal to the sum of the product of opposite lengths. So the product of these two sides plus the product of these two sides. So let's just keep it simple, and let's just let all of these side lengths here, we'll just all let them equal to DC. So then we have BD, which is also the same length as DC, times B. So DC times B plus DC itself times A is equal to the product of the diagonals. Now keep in mind, AD is just 2 times the length ID, which is 2DC. And then we multiply this with BC. We let BC equal C, so we'll just keep it as C. So now we can just pretty easily cancel out these DCs. And so that gives us that B plus A, or A plus B, is equal to 2C. Okay, so that's pretty cool now, right? So what we can do is now just solve this simple algebra expression for the product AB. So what we want here is the product AB. So let's just get rid of all this clutter and only focus on the algebra, right? We want the product AB. So, okay, let's go back. So we have ABC over 4 times some area, which we don't know, is equal to 13. And A plus B plus C over 2A equals 6. Now we know A plus B equals 2C from all the calculations we did. So we can plug that in here, right? So we have 3C is equal to 12A. So now we can solve for C, right? So that means that C is equal to 4A itself. Oh, sorry, I made a little mistake here. It's actually the opposite. It's 2A over A plus B plus C equals 6, right? Because the in radius here times the semi-perimeter is just equal to the area. So 6 times A plus B plus C over 2 equals area. So, my bad. Sorry I didn't catch that. But now we have the right expression. So now we still have A plus B equals 2C. So now we have A over, so we have 2A over 3C. So let me just write implies 2A over 3C is equal to 18, right? So now we can say, so 18 times 3, that's going to be equal to 54C. So 54C is equal to 2A. So that means that A is going to be equal to 27C. Oh no, that's a 6. This is a 6. I don't know why I wrote 18 there. 6 equals 6. So that means that A is equal to 9C. So now we can just plug that in here. So we have ABC over 9C, they conveniently cancel, is equal to 13. So, and then we multiply this by the extra 4. So we finally get that AB equals 36 times 13. And that gives us our final answer of 468.